Hi everyone. We continue in this video with Chapter 6, Geometry and Trigonometry, now with Section 6.3, Trigonometric Functions of Any Angle. In this section, we will extend the trigonometric ratios to all angles, allowing us to solve problems involving any size angle. So consider the point P on the terminal side of an angle theta in a standard position, as you can see here in this figure, such that R is the distance from the origin to P. If theta is an acute angle, then we can construct a right-angled triangle, POQ, as we can see in this figure over here. And we do that by dropping a perpendicular from P to point Q. So we can see that this line is perpendicular. And this point Q is obviously on the x-axis. So it follows that sine of theta is equal to y over r, right? Y over r, opposite over hypotenuse. Cosine of theta is going to be x over r, and then tangent of theta is going to be y over x, as long as x is not equal to 0. Extending this to angles other than acute angles allows us to define the trigonometric ratios for any angle, whether it is positive or negative. It is important to note that the values of the trigonometric ratios do not depend on the choice of the point P. If you have a point P prime as another point on the terminal side of angle theta, then triangles POQ, the big one, POQ, and P prime OQ prime, which is a smaller triangle, are similar, and the trigonometric ratios for corresponding angles are equal. So that means that, for example, tangent of theta is also equal to y prime over x prime. And the same thing for the other ratios. So now let's take a look at example 6.10. And it says, find the sine, cosine, and tangent of an angle alpha that contains the point -3, 4 on its terminal side when in standard position. So we can see -3, 4 on the terminal side of the angle alpha. So if we were to draw a perpendicular line here, we know that this distance is 3 units to the left, and this distance is 4 units up. We need to find r, or the hypotenuse, and we know that r is going to equal, from Pythagoras, the square root of 4 squared plus -3 squared. And this is going to be the square root of 25, which is equal to 5. So then we know that this distance here is 5 units. And then we're all set to write down the trigonometric ratios. So sine of alpha is going to equal 4 over 5. Cosine of alpha is going to equal -3 over 5. And tangent of alpha is going to equal 4 over -3, which we can write as -4 over 3. Next, we have example 6.11, and it says, find the sine, cosine, and tangent of the obtuse angle that measures 150 degrees. So, if we were to draw this on the Cartesian plane, 150 degrees is still 30 degrees short from 180 degrees, or pi, right, which is here. So if we draw a perpendicular here, we know from the special right triangles that this is a 30/60, and therefore this side would be length square root of 3. But because it's on the negative part of the x-axis, we have to use negative square root of 3. We also know that the other leg measures 1, and that the hypotenuse, or r, would have a measurement of 2 units. And then from here, we can find the ratios. So sine of 150 degrees is going to equal 1/2. Cosine of 150 degrees is going to equal negative square root of 3 over 2. And then tangent of 150 degrees is going to be 1 over negative square root of 3, which is the same as negative 1 over square root of 3. And this is going to be negative square root of 3 over 3. Now, we already knew these ratios, at least the ones for sine and cosine, from the unit circle. So that's something else we can use in this case, because we know the x and y coordinates for 150 degrees from the unit circle. Example 6.11 illustrates 3 trigonometric identities for angles whose sum is 180 degrees. In other words, a pair of supplementary angles. The following identities are true for any acute angle theta. So remember that acute means less than 90 degrees. We have that sine of 180 degrees minus theta is equal to sine of theta. We saw that in example 6.11, where sine of 150 degrees is equal to sine of 30 degrees, which equal 1/2. In the case of cosine, we have that cosine of 180 degrees minus theta is equal to minus cosine of theta. And that is very simple to explain, because if you look at the Cartesian plane, we know that here the coordinates for cosine are going to be positive, whereas in the second quadrant they are negative. And for the y coordinates, or sine, we know that here it's positive and here it is also positive. Whereas for tangent, it's the same as cosine. We have that tangent of 180 degrees minus theta is equal to minus tangent of theta. Now, since tangent of theta is equal to y over x, we can see that if we do y over x in the first quadrant, it's going to be positive. But if we do it in the second quadrant, tangent will be negative. So now let's go to example 6.12, and it says, given sine of theta is equal to 5 over 13, where theta is an angle between 90 degrees and 180 degrees, that means the second quadrant. Find the exact values of cosine of theta and tangent of theta. So if we draw a diagram of this, this is what it would look like. So notice that we have the values in the second quadrant. So we know that sine of theta is equal to y over r. That's why we have this 5 here, and we have this 13 here, since they told us that sine of theta is 5 over 13. But we still need x in order to find the exact values for cosine and tangent of theta. But from Pythagoras, we know that x is going to equal the square root of 13 squared minus 5 squared. And this equals the square root of 144, which is 12. So now we know that x has to be negative 12. Now it's negative because it's in the second quadrant. So We have then that cosine of theta is equal to negative 12 over 13, and that tangent of theta is equal to negative 5 over 12. Next, we have example 6.13. And for part A, it says, find the acute angle with the same sine ratio as 1, 135 degrees, and 2, 117 degrees. Part B says, find the acute angle with the same cosine ratio as 300 degrees and 2, 342 degrees. So for part A, let's recall that sine is positive in the first and the second quadrants. Hence, we have the identity sine of 180 degrees minus an angle theta is equal to sine of theta, where theta is an acute angle. Then we have that 180 degrees minus 135 degrees is going to equal 45 degrees. It follows then that sine of 135 degrees is equal to the sine of 45 degrees. So this is for part 1, for A. And then for part 2, we have that 180 minus 117 degrees is going to equal 63 degrees. Therefore, we have that sine of 117 degrees is equal to sine of 63 degrees. For cosine, we have that the x values in the Cartesian plane are positive in the first and fourth quadrants. So notice that we have an identity for cosine, which is cosine of 360 degrees minus an angle theta is equal to the cosine of the acute angle theta. So we have that 360 degrees minus 300 degrees is equal to 60 degrees. Therefore, cosine of 300 degrees is equal to cosine of 60 degrees. This is a fact that we already knew from the unit circle. And then for part 2, we have that 360 degrees minus 342 degrees is equal to 18 degrees. So cosine of 342 degrees is equal to cosine of 18 degrees. So now let's talk about areas of triangles. Now, if we look to this figure on the left-hand side, we are familiar with the standard formula for the area of a triangle. We know that the area of a triangle is equal to 1/2 times the base times the height. So for this particular case, the area is equal to 1/2 b, which is the base, times h, the height, also known as altitude. And h is a line segment perpendicular to the base, as we can see from here, and drawn to the vertex opposite the base. So this is the vertex opposite the base, and this is the perpendicular line that represents the height. Now, if we look to the triangle on the right-hand side, the height, because this triangle is obtuse, the height is actually outside the triangle, as you can see on this dotted line of the height of triangle ABC. We draw a perpendicular, and we have to extend the base here. So if the lengths of two sides of a triangle and the measure of the angle between these sides, which is also often called the included angle, if they are known, then the triangle is unique and has a fixed area. Therefore, we should be able to calculate the area from just these measurements, two sides and the included angle. This calculation is quite straightforward when the triangle is a right-angled triangle, and we know the lengths of the two legs on either side of the triangle. What we're going to do is develop a general formula that will apply to any triangle, whether it's right or acute or obtuse. So suppose that we know the lengths A and B, and we know the included angle C. So this is angle C. Let's suppose we know these three measurements. We know that the area for this triangle ABC is equal to 1/2 base times height. Now, we know that this thing here on the left, this angle here, is going to be 180 degrees minus C. And we know that the sine of 180 minus C is equal to H, the opposite side, over the hypotenuse, which is A. So that means that the height is equal to the sine of 180 minus C times A. But we also have the identity that says that sine of 180 minus C is equal to sine of C. So that means that the height is equal to sine of C times A. Now, if we substitute this into the formula for the area of a triangle, we can say that A is equal to 1/2 AB sine of C. So this is a very useful formula that, again, if we have two sides and an angle between them for any triangle, we can find the respective area. It's also important to notice that there are two more formulas that can be derived in the same way from this triangle. And it turns out that the area, or this formula, is also equal to 1/2. So we can also find the area with 1/2 A times C times the sine of B. So if we have sides A and C, and we have angle B, we can use the same formula. And this is also equal to 1/2 BC sine of A. So if we have B and C, and we have angle A, then we can use this formula instead. Let's continue with example 6.14, and it says, the circle shown has a radius of 1 centimeter, and the central angle theta subtends an arc of length 2 pi thirds centimeters. Find the area of the shaded region, a segment of the circle. So they want us to find the shaded region. First of all, let's remember that the formula for the area of a sector is 1/2 r squared times theta, where theta is the central angle in radians. Also, recall that the formula for an arc is equal to the radius times the central angle theta. But in this particular case, because the radius is equal to 1, we have that the subtended arc is equal to the central angle. So the central angle is 2 pi thirds. That means that the area of the sector, of all this sector, that would be including all of this, right? The area of the sector is going to be, so let's write area of the sector, is going to be 1/2 times 1 squared times 2 pi thirds, and this would give us pi thirds centimeters squared. But since they want us to find the area of the shaded region only, and this gives us the whole sector, we will need to subtract the area of this triangle here, right? And from the previous slide, we learned that the area of a triangle for which we have two sides and the included angle is going to be, so the area of the triangle is going to equal 1/2 times A times B, or 1 times 1, times the sine of 2 pi thirds. And this is equal to 1/2 times the sine of 2 pi thirds, which is square root of 3 over 2. And this is going to give us square root of 3 over 4 centimeters squared. So now we can do the subtraction. We know now that the area that we're looking for, the shaded region, is going to equal pi thirds minus square root of 3 fourths, which is the same as 4 pi minus 3 square root of 3 over 12. And if we plug this into the calculator and round to 3 significant figures, we are going to get approximately 0.614 centimeters squared. Again, rounded to 3 significant figures. So we continue with example 6.15, and it says, show that it is possible to construct two different triangles with an area of 35 centimeters squared that have sides measuring 8 centimeters and 13 centimeters. For each triangle, find the size of the included angle between the sides of 8 and 13 centimeters to the nearest tenth of a degree. So notice that we have two triangles. One is acute, this one to the left is acute, and this one to the right is obtuse. And they both have sides measuring 13 and 8 centimeters, and they have an included angle of alpha for this first case and beta for the second case. So notice that we can use the formula for the area of a triangle that says that for this case on the left, the area is equal to 1/2 13 times 8 times the sine of alpha, and that this should equal 35. So we're going to solve for alpha. So notice that this is the same as 4 times 13. That's going to be 52. So 52 sine of alpha is equal to 35. Therefore, sine of alpha is equal to 35 over 52. And then alpha is going to equal the inverse sine of the ratio 35 over 52. We make sure that our calculator is in degrees. We plug this in and we should get approximately 42.3 degrees. Now, this same fact would be true for the second triangle because we have the identity that says that sine of 180 degrees minus theta is equal to sine of theta. So beta should equal 180 minus 42.3 degrees. And beta would then be equal to 137.7 degrees to the nearest tenth of a degree. Now, because sine of 137.7 is equal to sine of 42.3, we therefore have that there are two different triangles with sides 8 centimeters and 13 centimeters that have an area of 35 centimeters squared. Again, one with the included angle of 42.3 degrees and the other one with an included angle of 137.7 degrees. Notice that your GDC will only give the acute angle value for the inverse sine function. In the following slide, you're going to find a few statements about equations of lines and angles between two lines. Recall that the gradient m of a non-vertical line is defined as, and this is on the Cartesian plane, m is equal to y2 minus y1 over x2 minus x1, and this is the same as saying the vertical change over the horizontal change. So if we look at this figure on the left-hand side, we have the equation y is equal to 1/2, that's the slope or the gradient, times x minus 1. So if the gradient is 1/2, it means that it goes up 1 and it moves 2 to the right. In other words, every time it moves 1 up, it will move 2 to the right. And then from this, we can draw a right-angled triangle with an angle theta. Now this is the case of finding the angle between the line and the x-axis. So for this, we can use the tangent function. Theta is then equal to the inverse tangent of m. For this particular case, the inverse tangent of 1/2, which is approximately 26.6 degrees. The same applies to this other case on the right-hand side, where we have the equation of the line being negative 1/2 x plus 1. Now in this case, it means that for every 1 unit the line goes up in the y direction, it moves 2 units to the left. So then this angle here, theta, the angle made between the line and the x-axis, is going to equal the inverse tangent of the slope or gradient, or the inverse tangent of minus 1/2, which in this case is negative 26.6 degrees. So now we're going to take a look at example 6.16, and it says find the acute angle between the lines y equals 3x and y equals negative x. So this is the line with equation y equals 3x, and this is the other line with equation y equals negative x. So they want us to find the acute angle between them, which is theta. But to solve for theta, first we will need to find alpha and beta. And we can find those measurements using inverse tangent. So we know that angle alpha is going to equal the inverse tangent of the slope, which for this case is 3. If you plug that in the calculator, you're going to get approximately 71.565 degrees. And here you want to carry a few decimals in order to get a more accurate answer. Beta, on the other hand, is going to equal the inverse tangent of the slope of the other line, which is -1, and this is equal to -45 degrees. So notice that theta is going to equal 180 degrees minus, why 180 degrees? Because all of this is 180 degrees, half a circle, minus alpha plus the absolute value of beta. Why the absolute value of beta? Because we found a negative angle, which makes sense because if you go in this direction, it's going to be a negative angle. But for the purposes of solving this problem, we actually need to find the sum of alpha and the absolute value of beta. Therefore, theta is going to equal 180 degrees minus 71.565 degrees plus 45 degrees. And here we're going to get that theta is going to be approximately 63.4 degrees, rounded to 3 significant figures. So now let's do example 6.17, and it says find the acute angle between the lines y equals 5x minus 2 and y equals 1/3 x minus 1. So again, the acute angle between the lines is going to be here theta. But in order to solve for theta, we need to find alpha and beta. Notice that a horizontal dotted line, this one over here, is drawn through the point of intersection between the two lines, because the slope is going to be in reference to a horizontal. So alpha is going to equal the inverse tangent of the slope of the first line, 5x minus 2. So inverse tangent of 5. And this is going to give us approximately 78.690 degrees. So again, we carry 3 decimals here. Then we have that beta is equal to the inverse tangent of its slope of the second line, which is 1/3. And here we get approximately 18.435 degrees. So notice that theta, the acute angle, is going to equal alpha minus beta, because all of this is alpha, and if we subtract this section here, this angle, we're going to be left with theta. So theta is equal to 78.690 degrees minus 18.435 degrees. And then we have that theta is approximately 60.3 degrees, again rounded to 3 significant figures. So now let's take a look at example 6.18, and for part A, it says find the exact equation of line L1 that passes through the origin and makes an angle of minus 60 degrees or 120 degrees with the positive direction of the x-axis. So that means with this here, the positive direction of the x-axis. So because it goes through the origin, it doesn't have a y-intercept. So that simplifies the problem quite a bit, because y is simply going to equal sum m, a slope, times x. But we know that m is equal to the tangent of the angle. So in this case, negative 60 degrees. It could also be tangent of 120 degrees because they are equal. So y is equal to the tangent of negative 60 degrees times x. And if we solve for the tangent of negative 60 degrees, we're going to get that y is equal to minus square root of 3 times x. Next, we're going to focus on part B of the same question, 6.18. So it says the equation of line 2 is 7x plus y plus 1 is equal to 0. So they give it to us in the standard form. Find the acute angle between L1 and L2. So again, the acute angle is going to be this one over here, theta. And notice that we draw a dotted line, a horizontal dotted line that goes through the intersection of both lines. From part A, we already know that this angle here is negative 60 degrees. And we need to find this angle, alpha, which is the angle between the horizontal and line 2. So let's start with that. Alpha is going to equal the inverse tangent of the slope of line 2. But to find out what the slope of line 2 is, we need to rearrange this equation over here. So notice that we can rewrite this as y is equal to minus 7x minus 1. Therefore, the slope is minus 7. So alpha is going to equal the inverse tangent of minus 7. And that's going to be approximately negative 81.870 degrees. So theta is going to equal, and we're going to use the absolute value of this, is going to equal 81.870 degrees minus the 60 degrees that we know from before, this over here. So we're using positive values because we need a positive answer, right? So this is going to equal, for theta, approximately 21.9 degrees rounded to 3 significant figures. So now we're going to do example 6.19, which is the last one on this video. And it says, the diagram shows a pyramid with a square base. It is a right pyramid, so the line segment, or the height, drawn from the top vertex A is perpendicular to the base. So we can see that here. And will intersect the square base at its center C, which is right there. Each side of the square base has a length of 2 centimeters. So we can see that here, 2 centimeters, 2 centimeters, 2 centimeters, and 2 centimeters. And the height of the pyramid is also 2 centimeters. So this is the height. Find, part A, the size of angle AGF. So AGF is the size of this angle here. So we can label the midpoint of GF as point M right here and draw 2 line segments, CM, which is this over here, and AM, which is from the vertex to the midpoint M. Since C is the center of the square base, then CM is equal to 1 centimeter, which is right here. We can extract the right-angled triangle ACM, so the one we see in blue here, ACM, to find the length of AM, or the slanted height of the face of the pyramid. So notice that AM with Pythagoras is equal to the square root of 1 squared plus 2 squared, which is the square root of 5. And AM is perpendicular to GF. Now we can extract the triangle AMG, which is this one, AMG, and we're going to separate it from the rest of the figure so we can take a good look at it. So here we have AGM, and we're going to use the tangent ratio to find the angle AGM, which is this one over here. So we use tangent, as I said, tangent of angle AGM is equal to the square root of 5 over 1, opposite over adjacent. Therefore, the angle AGM is equal to the inverse tangent of the square root of 5, which is approximately 65.9 degrees to 3 significant figures. So now let's erase a bit and focus on part B. So for part B, they want us to find the total surface area of the pyramid. Now the pyramid is comprised of a square base and then 4 faces that are triangles, which are identical. So we need to find the area of triangle AGF. So the area of triangle AGF. And this is going to equal 1/2 times the base, which we know is 2, times the height, which is the slanted height of the pyramid, which we found to be square root of 5. So this is square root of 5, which is the area of each one of those 4 triangles. So now we can find the total area. So the surface area of the pyramid is going to equal the area of the square base, which is 2 squared, plus 4 triangles that are equal to this one that we found here, AGF. So 4 times square root of 5. And this is equal to 4 plus 4 square root of 5, which is approximately 12.94 centimeters squared.